Mr. Tarrou, in the next few lessons, we are going to be looking at trigonometric integrals. In the first of probably 3 videos, we're going to be looking at guidelines for evaluating integrals involving powers of sine and cosine. In our next lesson, we're going to be dealing with evaluating integrals that involve powers of secant and tangent. And then I'm going to throw in a third lesson, just to add in a few more. What we learn when dealing with powers of tangent and secant is that they're a little bit tricky. It's just because of the way the derivative and integrals work with those particular trig functions. And what you learn with dealing with secant and tangent is going to allow you to involve or deal with integrals involving cotangent and cosecant. But we'll just throw in a few extra kind of tricky ones in the last lesson. You're going to find links to those 3 lessons, or, well, this is one of the 3, so you'll find links to the other 2 lessons in the description of this video. And you'll also find timestamps to the 5 examples that we are going to do in this lesson in case I happen to start one that you find to be a little bit too easy or you just want to skip ahead because I maybe talk a little bit too much. Okay, so guidelines for evaluating integrals involving powers of sine and cosine. You'll find directions like this probably in your calculus book. If the power of sine is odd and positive, then save one sine factor and convert the other remaining factors to cosine, expand, and integrate. Now, we're looking for that power of sine, and in step 2, let's go ahead and read that. If the power of cosine is odd and positive, save one cosine factor and convert the remaining factors to sines, expand, and then integrate, and you have some notation to go along with that part of this part B of these guidelines as well. And we're looking for that odd power, whether it be on sine or cosine, and saving it, and then converting the remaining to the other trig function. If you have an odd power of sine, convert to cosine, and if you have an odd power of cosine, convert the remaining to sine, is because we're going to be using the power rule to integrate or evaluate these indefinite integrals. And we're going to be converting between sine and cosine using the Pythagorean identity. So we have a 2k plus 1 here indicating math notation, of course, for that general idea of something being odd. We're going to remember that when we add exponents, that happens when we multiply like bases. So the sine of 2k plus 1 is broken up into basically the sine of 2k times the sine of x to the first power. And there's your 2k plus 1. When you multiply like bases, you add those exponents. And we see that inside what is now going to be an even power, we have sine squared, or inside this power, this even power of k, we have the cosine squared, because we're using, the Pythagorean identity, sine squared plus cosine squared is equal to 1, to go from an even power, or sine squared, not just even, but a sine of x squared to 1 minus cosine of x squared. And then again to that power of k. And then what you're going to see here, at least in this particular line, is we're going to take this binomial and raise it to some kind of power. So we'll have a bunch of cosines in here and multiply with this cosine to a particular power, and then you have this sine of x. So all of these cosines are basically going to be like your u raised to a higher power, and then u prime or du is going to be your sine of x, or at least in some form of. The derivative of cosine is negative sine. So that's going to act as sort of, with an addition of a negative, our u prime. Now, if the powers of both sine and cosine are even, and really this is true if you just have one trig function in your integrand that for sine and cosine that has that even power, we're going to repeatedly use these identities. These are the power reducing identities that you may have been introduced to in pre-calculus, to convert the integrand to odd powers of the cosine, because you can see sine squared of x is equal to 1 minus cosine of 2x over 2, and cosine squared still is going to leave you with a with the trig function of cosine in that new expression. So we're going to be converting the integrand to odd powers of cosine, and then go back to step B, which is to, again, understand that we're looking at a cosine factor with an odd power, saving 1, and then converting everything else into terms of sine. Now, if all this seems a little bit confusing, hopefully it won't after you get through our 5 examples coming up right now. So like always with my videos, I will tend to go from easy to hard, and here we are looking at our easiest example of the 5. We're going to find the indefinite integral of sine of 3x to the 5th power times the cosine of 3x dx. Now, don't read those guidelines too literal, because you'll see that we have the sine of 3x being raised to an odd power. So let's, save one of those signs and convert the remaining signs into cosine. But see, this is actually what we want our integrands to basically look at, to finish the integration problem, which is we've got a trig function raised to a power, and then there's another trig function that's just to a singular power. Like, what we're looking at basically is the sine of something being raised to the 5th power. There's a function inside that power of 5. So let's let that be u. And then du is going to be, well, the derivative of sine, of course, is cosine. And then inside the sine function, we have another function than just beyond a simple x, which is 3x. And using the chain rule, of course, the derivative of 3x is just simply equal to 3. So see, there we can see now that we are looking at a u that's inside our power of 5, and then our u prime or du, whatever you want to label it as, that chain rule pattern, that cosine of 3x. Now, I'm showing that I'm starting a u substitution, but I'm not going to write these like I would do early in my calculus class when I'm teaching it, where I put everything in terms of u and make it exactly match the rules. So I'm going to do a little bit of pattern recognition of that chain rule. So if my u is the sine of 3x, then my du is 3 cosine of 3x. So I need to have a u, to have a complete u prime or du to exactly match that expression, I need to introduce that multiple of 3, which I'm going to cancel out or balance out with the division of 3. And we get 1/3 to balance out the multiplication of 3 I'm going to put in here, of 3 times the sine of 3x to the 5th power times the cosine of 3x dx. And now that I've written that, if you really want to make that du factor or that u prime factor stand out, I guess you could take, I'm going to generally tend to put the 3 first in my notes, but you could keep that with the cosine to make the du or u prime notation or factor in your integrand stand out even more. There you go. And again, here is our u inside the power of 5, and all of this is our, as you can see here, our, whoops, I forgot that dx in my last lesson as well. I can't continue to do that. There is our du. Okay, so there's our chain rule complete, and we're ready to just simply integrate using the power rule, which is to raise this power by 1 and then divide. So we're looking at 1/3 times raising the power of 5 by 1, we get 1/6, because we need to divide then by that increased power, times the sine of 3x to now the 6th power, plus, don't forget your constant of integration, and our final answer is 1/18 sine of 3x to the 6th power plus c. And that is the end of our first example. Now over here, now we're getting into the type of questions that we're going to be dealing with the rest of our examples, even in our next video when we get into powers of secant and tangent, where I basically need to make this integrand look something to the form of this one, where there's a trig function, sine or cosine for this lesson, raised to a power, and then that du off to the side. Now, we have sine being raised to the even power. Our guidelines said to find the trig function raised to the odd power, remove one of those, and convert the remaining even powers to the other trig function. So we're going to say that this is equal to the indefinite integrand of, let's see, I could, just thinking about how I want to write this, cosine of 2x times the cosine squared of 2x. I like to show all the steps, which your textbook may skip. So hopefully you appreciate all these steps I'm showing. So here I am pulling at that odd sort of extra power of cosine. Now we have a cosine squared of 2x. We're going to use the Pythagorean identity to rewrite that in terms of sine. Okay, now at this point what I'm going to do is I'm going to take this cosine of 2x and the sine of 2x raised to the 6th power and take these factors and distribute it through these parentheses. So, you know, maybe now I should have, whatever, maybe kept the cosine squared first so it'd be more easily showing this distributive property. But these two factors coming together are going to get multiplied to the 1 and then the minus sine of 2x. Excellent. Now, again, showing every single small step to help you understand this as much as possible, and honestly, I need this as well. I find it a little bit more tedious in the amount of steps and time that I have to take to do these problems, but I do like to take these separate terms that we're developing and give each one of them their own integral notation, or separate the integrands to make the rest of this process a little bit you know, easier. And now you can see that we've got kind of two separate integrands or integrals that are in the same format as our first example. So I'm just going to step off and reveal this one step at a time to speed up our lesson. So not too much to talk about because the rest of this is so similar to example 1. Just like to point out here, when you separate these integrals, I find it easier to see, you know, to more clearly see how you're going to have possibly different coefficients on your multiple terms when you do or go through the rest of your integration process. Now let's get to example 3 and the phone. Alrighty then, so for example 3, we have the indefinite integral of the sine of 4x raised to the 5th power times the cosine of 4x raised to the negative 1/2 power dx. And really, this example is also similar to the first 3. You're just stepping them up a little bit in difficulty. And because of that, I'm not going to walk through this whole thing. Like the second example, we'll get it started. I'll reveal the rest of the solution one step at a time and maybe give you the opportunity to pause the video lesson and maybe try it on your own before I reveal the solution. Now examples 4 and 5, those are going to start to vary compared to these first 3. Now I included this one because it's a little bit scary with maybe with your power of cosine being a negative and having that fractional power on it, but don't worry about it, it's not going to be a big deal. And because we still have a sine with an odd power on it, so we can still remove that sort of odd power of sine, break it down to a power of 4, and we get the indefinite integral of the sine of 4x. And this is the second reason why I included this particular example. Now, this odd power is not just an odd power of 3, it's an odd power of 4. So we're going to have to do a little bit more work to get that broken down into a power of 2 and a little bit of expansion so that, you know, we can use the Pythagorean identity, which has sine squared, power of 2 plus cosine squared is equal to 1. So what we're going to do here is not write that as sine of the 4th, but we're going to write that as sine squared of 4x. And again, if we've taken that one power out, this should be a power of 4, so squared and another power of 2, those stacked powers are going to, of course, ultimately be, you know, sine of 4x to the 4th power. Now we have cosine of 4x to the negative 1/2 power. We're going to, with the Pythagorean identity, change that to 1 minus cosine squared. Now at this point, this is where I'm going to step off and start revealing the solution one step at a time to keep this lesson as short as possible, yet have a bunch of examples in it, plus give you the opportunity to go ahead and finish this. We're going to take this binomial raise it to a power of 2, which of course is going to give us a trinomial, and then take this sine of 4x and this cosine of 4x to the negative 1/2 power and distribute it through those three terms and create three separate indefinite integral or three separate integrands and finish the problem up. For example 4, we're going to find the indefinite integral of sine of 2x raised to the 4th power dx. Now, with this one only having a sine function that is raised to a power, well, that function, that sine function inside the power means we need a u prime, or the derivative of sine is cosine. We need a cosine. Now, we want to, in this example, and actually the last example, the last two, we're going to be dealing with those power reducing formulas to help us get this integrand into some kind of format that we could, work through the integral. And you want to use the power reducing identity, or the power reducing formulas or identities, because we could write sine squared of 2x times a sine squared of 2x, and then use Pythagorean identity to write that as sine squared of 2x times 1 minus cosine squared of 2x. The issue with that is you've got, a couple of even powers. Now, with those power reducing formulas, then in us having sine functions and cosine functions within the same integrand that both have even powers, we could still use these power reducing formulas to get us out of that jam of both of these having even powers. But there's no reason why we can't just do that right off of the start. So we're going to write this as the indefinite integral of the sine. Actually, let's go ahead and do that. The sine squared of 2x times the sine squared of 2x dx. You could also write that as the sine of 2x squared raised to the second power, which actually is what I did in my notes. And then bring in this power reducing formula to get 1 minus, write that sine squared of x to be 1 minus cosine of 2x over 2. Now, this is a single angle, and this is a double angle already. That doesn't make any difference. Just whatever this angle is, double it as you apply and work through that power reducing formula. So we're going to have the indefinite integral of 1 minus, for this sine squared of 2x, 1 minus the cosine, doubling that 2x, we get 4x over 2 times, again, 1 minus cosine of 4x over 2 dx. Now distribute these two factors together. 2 times 2 is 4. And because we're taking 1 minus cosine of 4x times 1 minus cosine of 4x, or effectively just squaring a binomial, we're going to get 3 terms. I'm going to go ahead and write that that product of 4 under each just said that twice, underneath each of those 3 terms, and separate it all out. Great, well, I went ahead and did that, but as you can see, we still have a cosine squared. We still have that term that's going to have, just the one trig function with an even power on it. So we're going to go ahead and apply that power reducing formula one more time. Okay, now at this point, what we have left to do is we're going to see, we just have now cosine functions with no power on them. So as I do a little bit of expansion with this remaining term and combining a couple like terms, because we're going to have a 1/4 times 1/2 is 1/8 along with this 1/4. So I'm going to step off, clean this up a little bit, and just not have to do anything real complicated to finish the problem out because our trig functions are just simply to the first power. We know the integral of cosine is inverse sine. No, excuse me. The integral of cosine is sine. So there we go. We went ahead and took that 1/4 times 1/2 and got 1/8. And again, 1/4 times another 1/2, that separate term of cosine of 8x, giving us 1/8 cosine of 8x. Again, like I like to do, it's a little bit tedious, but giving each one of these, or writing a separate integral for each of these terms, and of course 1/4 and 1/8 is 3/8 after you find common denominators, I'm bringing the coefficients of negative 1/2 out in front and 1/8 in front of these integral symbols. And with the, with our cosine functions, in here we have an inside cosine function of 4x, and the derivative of 4x is equal to 4. So I've got my u and my u prime there with my 4 dx. And if I introduce a multiplication of 4, cancel that with or balance that with a division of 4, and likewise introduce a multiplication of 8 to finish the chain rule, you want to divide by 8 and just integrate each of these actually pretty straightforward integrals now, and get in our final answer of 3/8 x minus 1/8 of sine of 4x plus 1/64 of the sine of 8x plus c. Now our last example again is going to require the use of one of these power reducing formulas, and it's also going to require that we remember how to do integration by parts. It's our last example. Example number 5. We have the indefinite integral of x times cosine of x squared dx. Now, like I said, our last example, most complicated. We're going to have to do one of our power reducing formulas and finish up with integration by parts. But you wouldn't know that when you first glance at the problem. So let's start working through it and see what happens. We have that one trig function raised to an even power. Just like our previous problem, we need to break that down with the power reducing formulas. So we're going to have the indefinite integral of x times, well, cosine squared of x is 1 plus cosine of 2x over 2. Excellent. And we have just sort of one big ugly term, but inside this fraction, the numerator has two separate terms. So we're going to distribute the x and break this one big integrand up into smaller, easier to deal with pieces. So we're going to have x times 1/2 is, and I'm going to pull the 1/2 out front as well, 1/2 times the indefinite integral of x dx. We have a plus sign here. And we also have a coefficient of 1 in front of the cosine of 2x and a 2 in the denominator. I'm going to pull that 1/2 out. And then x times the cosine of 2x dx. Awesome. Well, this first part's going to be easy enough to deal with. The integral of x is simply 1/2 x squared plus c. And over here, though, we have x times the cosine of 2x. So you might glance at that initially and just go, okay, well, my cosine function has an inside function of 2x. The derivative of 2x is equal to 2. But I don't have a factor of 2, or just not another factor at all, or maybe a constant. I have another factor of x. So we're not going to easily be able to get this inside function of 2x with the derivative of that just being x 2, and us having another factor of x to deal with. It's an integral of two functions being multiplied together, which is great if one function is a derivative of the other function, like we've been doing through this whole video, like the derivative of sine is cosine. That's where we're working through. But with those, with this inside function and that not being the derivative of that inside function, we have to go through the integration by parts. Now the integration by parts, I'll put a link to that video right here and in the description of this lesson if you want to go review this process. But the integral of u dv is equal to uv minus the indefinite integral of v du. And what you want to do is you want to look through this integrand and look for the most complicated portion of it, or the most complicated factor that can be integrated using our basic integration rules. Now that's going to be the cosine of 2x, but you can also use the acronym LEATE, at least that's how I said it in my lesson, to help you come up with some ideas or go through a little bit of a process to try and choose what should be or what may be your best choice for dv. And that's going to be your logarithms, inverse trig functions, just algebraic expressions, trigonometric expressions, and your exponential functions. Now, we have a trig expression. It is the cosine of 2x. So we're going to let dv equal the cosine of 2x. And when you go through trying to find an appropriate substitution for dv, don't forget to bring along the dx. That always goes together. So that means that v is going to be equal to the indefinite integral of the cosine of 2x dx. We have a inside function of 2x. To finish that chain rule, the derivative of 2x, like we mentioned before, over here is just simply 2. So we have v is equal to 1/2 times the indefinite integral, kind of sloppy there, sorry, of 2 times the cosine of 2x dx. Well, of course, with our chain rule completed, the integral of cosine is sine, and we have v is equal to 1/2 the sine of 2x. Now, normally you would need your plus c in there as well, but we'll deal with that constant of integration as we finish up the end of our problem. Now, let's see here. We had a good substitution for dv that allowed us to find v, but we need a u and a du. Well, if all of this portion of our integral, this factor is our dv, then the remaining factor needs to be our u. So u, and I want to make sure I don't run out of room here, is equal to x, then du is going to be equal to 1. Now, normally, okay, so that means that we're looking at, and I'm going to do all the integration at once. So we're going to be looking at 1/2 the indefinite integral of x dx plus this 1/2 here. Now I'm going to put a big old bracket because this integral is being broken up into two terms. I want to make sure that that factor of 1/2 gets distributed to both of those. So we're looking at u times v. So u times v. So we're looking at x over 2 times the sine of 2x minus the indefinite integral of v du. Okay, well, v du is going to be 1/2 sine of 2x, and now I'm realizing that I probably should have went ahead and put that dx there so we can include it with the statement, because of course we need a dx notation with our indefinite integral. Okay, now, so sorry about the misspeaking there a little bit. I'm going to go ahead and pull this 1/2 out front just to show you every little minute step, and I also need to finish that chain rule. So I'm going to bring the 1/2 out front. I'm going to finish that chain rule by letting u or w or whatever letter you want to pick now be 2x. So I need a 2 out here and a division of 1/2, or division of 2, excuse me, to cancel that out. And other than taking the integral of sine, which is negative cosine, because that chain rule is finished, I can pretty much just write the answer and then distribute the factor of 1/2 there. So we got 1/2. The integral of x is 1/2 x squared, so we're going to have 1/2 times 1/2 x squared plus 1/2 times x over 2 sine of 2x. This is going to be 1/4, but the integral of sine is negative cosine, so we're going to have plus 1/4 cosine of 2x. And now I'm going to go ahead and put my constant of integration in here. I could put it here or outside. Probably better just to put it outside, because when I multiply by 1/2, I'm just going to make another unknown constant. And our final answer is going to be 1/4 x squared plus x over 4 sine of 2x, and then plus 1/8 cosine of 2x plus c. Just trying very hard not to make any careless mistakes. And I pre-work all my homeworks or my examples, so let's just make sure I didn't. I've got 1/4 x squared plus x over 4 sine of 2x plus 1/8 cosine of 2x plus c. And that is the end of my last example and this lesson dealing with integrals, trigonometric integrals that involve powers of sine and cosine. As soon as it's ready, we'll have a link in the description again of trigonometric integrals that involve powers of tangent and secant. I'm Mr. Tarrou. Bam! Go do your homework.